Hello, we are ME14, and welcome to our presentation on the channel lock forging cell. I'm Coy Bardwell.
I'm Nathan Lee.
I'm Jacob Sack.
And I'm Jonathan Vioral.
So a little bit of background on this project. Channel Lock is an American manufacturer of hand tools, primarily recognized for its high quality tongue and groove pliers. This project specifically focuses on the robotic automated forging cell that is used to make the 14-inch, 16-inch, and 18-inch pliers. The main issues they're finding within their forging cell that we took a look at was the forging robot that's used to manipulate the billet between the forging die and hammer. The bottom gripper fasteners become loose after unknown number of billets, creating substandard parts. Another issue we looked at was the trimming die, which currently has half the life of the forging die, so looking into increasing the life. And then finally, the last concern is the forging die life. Further research investigating the forging die into the manufacturer guidelines to show optimal running temperatures and preheating temperatures.
For the forging robot, there's a gripper on it that we decided to look at and design. And the final design that we went with was what you see on the right, with fasteners loaded in from the side. We used ANSYS FEA to determine the stresses acting on the pin and the gripper of the design. And we also did fatigue calculations to ensure that the life would last for an extended period of time. And we wanted this to be greater than the current design. Along with that, we would want a safety factor over 1.5. We produced a prototype during this project as well, which you can see is slightly different from the final design we just mentioned. And this was done because the manufacturing needs could be done during the timeline of the project. And prior to prototyping, we made sure that FEA calculations and fatigue calculations were completed to ensure that it wouldn't fail and that it displayed a factor of safety over 1.5.
Another thing that we investigated was the weld repair on the trimming die. So a series of welding samples were gathered to perform hardness testing and also look at the weld penetration into the base material depending on each experiment. We conducted 4 different experiments, each with different conditions. One of these experiments included heat treating the die to provide a more uniform hardness in the weld and see how else it would affect material properties. And from these experiments, we found that preheating will give better weld penetration, which should decrease stress concentrations, resulting in an increased fatigue life for the trimming die. And we also concluded that heat treating would not affect the weld penetration.
So for the forging die, we used manufacturer guidelines and research and recommendations to make recommendations to increase the life of the forging die. From that, we see that what is currently being used was compared to the manufacturer's guidelines. We see that the temperatures that they were used running were not reaching the manufacturer's guidelines, so we were able to make recommendations to reach that and increase the life of the forging dies. In conclusion, a new gripper design was created to improve the life of the fasteners as well as a new fastener type with the new design. Testing was completed on the welding of the trimmer die, and an SOP was made to increase the life of the cutting edge and the penetration of the weld of the cutting edge, and a forging die recommendations were made based on the current state and background research.